Hello everyone, in today's video we will see the approximate vertex cover that is an approximate solution for the vertex cover problem, and it's not the optimal solution but still a good solution. We will use an algorithm called two-approx algorithm that will find a solution, will return a solution that is at most twice the optimal solution. We will see in detail what does this mean, but first let's see what is the vertex cover problem in a graph, and then we will try to apply the two-approx algorithm on this graph. Let's call it G. So the vertex cover in its optimization version says the following. Find a subset of the graph's vertices. The vertices are A, B, C, D, E, F, and G. So find a subset of the graph's vertices that covers all the edges, meaning that for every edge in the graph, at least one of its endpoints is included in the vertex cover. While the vertex cover decision version says the following. Does G have a vertex cover of size k? Yes or no? So the answer in the decision version will be simply yes or no, while in the optimization version it asks to effectively find a subset. So that's what makes it difficult in the optimization version, because we are required to find this subset. So what does it mean, find a subset of the graph's vertices that covers all the edges? Well, it means that in a graph, eventually there will be some vertices or nodes that are extra. So, for example, consider that if we remove node A, the vertex A, we still have B, and B allows us to touch this edge 1, but also this edge 2. So if we remove A, nothing changes because we still can touch this edge and this edge, for example. And so on. So we are trying to remove the unnecessary nodes or vertices in order to still have the possibility to touch all the edges. Now, the two approximation algorithm, that is a greedy algorithm, works in the following way. These are the steps that we need to repeat in order to find an approximate solution for the vertex cover problem, for the vertex cover optimization problem, optimization version of the problem. Okay, let's try it. So, start with an empty vertex cover C. It means that we will have a set C that will contain 0 vertices at first, while we iterate over the input graph G. We will start to fill this C set until no edges remain, and we will see right now what this means. So start with an empty vertex cover C, and we have it here on the right. Pick any edge UV from the graph randomly. So let's pick one. Suppose the edge 1 that is between A and B. Let's pick that. And we can add it to C. So C will contain now the vertices that this edge touches. The vertices are also called endpoints. So if we take randomly this edge one, the endpoints or vertices or nodes that this edge touches are A and B. So pick any edge UV from the graph randomly. Add both vertices U and V to C. So we add A and B to C. Right, okay. Remove all the edges incident to U or V from the graph. So we have to remove 1 and 2. Well, let's totally remove them. And repeat this until no edges remain. So now we have to redo this. So randomly select an edge of the remaining graph. Let's pick this one randomly, 7. Well, now the endpoints are A and D, right? So we have to add A and D to the set C. So we will have A, B, E, and D. Sorry, E. Well, now we have to remove all the edges that are incident, so that touch E and D. Let's do it. We can remove this one, this one, this one, this one, this one, and this one. There are no more edges. So our set C is filled with A, B, E, and D. This is the approximate vertex cover. Is not the optimal solution. The optimal solution, let's call it C. C star. This is the approximate solution. Approx solution sol. This is the optimal solution. Optimal solution. And we have that the result, the vertices in C form a vertex cover, and the size of C will be at most twice the size of the minimum vertex cover. Okay. Now let's talk a little bit about the approximation ratio. This one. Well, the approximation ratio of an algorithm is a way to measure how close the solution it produces is to the best possible solution called the optimal solution. In simple terms, in this max ratio less than or equal rho of n, C is the cost or value of the solution that the algorithm finds, in this case the 2-approx algorithm. C star is the cost of the optimal best solution. The algorithm solution is considered good if the ratio between these two costs is within a certain factor, rho of n, where n is the input size. This is the formula, and this means that the algorithm solution is at most rho of n times worse than the optimal solution. If the algorithm guarantees this for all inputs, it's called a rho of n approximation algorithm. If rho of n equals 2, the algorithm guarantees that its solution will be no worse than twice the optimal solution. So, let's see why this works, why this set of vertices C works, this approximate vertex cover. A, B, E, and D means that by considering these vertices A, B, E, and D, we can touch, we can visit all the edges in the graph. And let's see this in action. Let's take back the original graph with all the edges, yes. Okay. And so A, B, E, and D. Well, let's see. So, thanks to node or vertex A, we can touch this edge 1. Thanks to vertex B or node B, we can touch the edge 2. Thanks to D, we can touch edge 8, 3, 7, 6. So we cover all this. Here we cover this. And now, thanks to the vertex E, we cover 4, also 7, but it's already covered by D, and 5. So we have this and this. This set of nodes allows us to touch all the edges in the graph. So we can remove the other nodes. For example, we don't need G, we don't need F, we don't need C. Of course, this is one of the solutions. There may be others. You can find them by applying another time the algorithm and eventually choosing randomly other edges in the graph. Now let's see something interesting. Is that here we have that C is made by A, B, E, and D. So the approximate vertex cover is this. Eventually we can have even a better solution by considering only these vertices B, D, and E. Let's see why. So B, D, and E is like the minimum vertex cover, so the optimal solution, this. Let's clear a little bit the board and let's see why that works and why it is minimal. So, B. If we consider the vertex B, we can touch edge 2 and edge 1. If we consider the vertex D, we can touch this, 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 and this. And if we consider E, we can touch this and this. And yeah, that's it. As you can see, with only 3 vertices, only 3 nodes, we can still touch all the edges in the graph. So, we have that this is made by 3 elements. And now we will take a look at the proof that shows us how and why this algorithm, this true approximation algorithm, will find a vertex cover that will be at most twice the size of the minimum vertex cover. Alright, so we can say that this algorithm, true approximation algorithm, or approx vertex cover, runs in big O of absolute value of the vertices plus absolute value of the edges time. Then this algorithm returns a set whose size is at most twice the size of an optimal solution. And let's call A the set of edges that are randomly picked by the algorithm during the execution. Then we have that no two edges in A share the same endpoint. No two edges between those randomly picked, no two edges in A share the same endpoint. An endpoint is a vertex, a node. So C equals the absolute value of C, so the number of elements in C, that in our case was 4, equals 2 times the absolute value of A. What does it mean? That in our case, during the execution, we randomly picked only 2 edges. If you remember, we picked 1 and 7. So A in our case was 1 and 7. Absolute value of A was 2. So, no two edges in A share the same endpoint, hence the absolute value of C equals 2 times the absolute value of A, and in our case, C equals 2 times 2, 4. And as you can see, C equals 4, because we have A, B, E, and D. In our case, C is made by A, B, E, and D. So the size of the vertex cover set C is twice the number of edges in A, and mathematically is this. Now, we have that any vertex cover must include at least one endpoint or one vertex or one node of each edge in A. Hence, the absolute value of the optimal solution, C star, is greater than or equal the absolute value of A, where A was the set of edges that were randomly picked by the algorithm during the execution. So the cost of the optimal solution, C star, is greater than or equal A. So what does it mean? It means that the number of nodes must be at least the number of edges. Finally, two times the absolute value of A equals C, that is less than or equal 2 times C star. Then this tells us that the cost of the approximate vertex cover is at most twice the optimal solution, because in our case A was 2, so we had 2 times 2, so 4, right? 4 equals C, the absolute value, sorry, I forgot the absolute value here. So we have 2 times 2, 2 times 2, 4. C has length 4 because was made by A, B, E, and D. And we have that 4 is less than or equal 2 times the absolute value of the optimal solution, that in our case was B, D, and E. So 3. So we have that 4 is indeed less than or equal 2 times, let's do it, less than or equal 6. So this tells us that C, that is the solution found by the true approximation algorithm, will be at most twice the solution found by an optimal algorithm, and yeah, that's it. This is the approximate vertex cover. This was the true approximation algorithm, approximation ratio, and for today I think that is more than enough.